All right, so welcome everyone to the second part of Nate Lesnevich talk on combinatorics of GKM theory and the dot auction.
Well, thank you all for sticking around. Um, yeah, let's get going. So this is the summary of the structure that I just left on, right? Continuing forward, right? So what's like the big overarching goal in this area, right? I want to be able to compute the graded pieces of this character only using the combinatorial data of what transpositions we're allowed to use. Right. So what I'll talk to you today, some of the results that I'll be able to share with you, right? First, we'll be able to say something about module generators when we have a minimal generating set of transpositions, right? So this can be the permutahedral case, right? Uh, the simple transpositions are a minimal set of generators for whatever vial group you're working with. But this is going to work out for any minimal set of generating transpositions, regardless of whether or not it actually corresponds to like a geometric object. Right? Uh, we're going to be able to compute the first degree graded character for any transposition set in type A. So when we're working with the symmetric group, that first graded piece, we're going to be able to compute uh, everything that we want for any set of transpositions, right? Regardless of whether or not they correspond to some sort of geometry. Right. And finally, we'll be able to do the same computation specifically in the geometric case, right? The one that corresponds to Hessenberg variety, regular semi-simple Hessenberg varieties in types B and type C, right? So what are sort of the big hurdles that we have to jump over here? Right. Well, for one, if we just take any set of transpositions to build our graph and then work with this module of splines, we might not have any geometry to help us out, right? We can't pull things like dimension from known results. We sort of have to work totally algebraic on spline side. Uh, And it turns out that the algebraic properties of that set can get sort of wild when they're not constrained by being associated to this geometry. And the big hurdle for types B and C, even just staying inside of a geometric context, is that we don't have any chromatic symmetric function connection to work with. So in type A, there are like really well studied Shresian walks, Gay-Piquet, Brosnan, and Chow combinatorial setup that you can use to compute these graded characters without working with any splines or really any geometry at all. That doesn't exist in any other type. Uh, so one of the problems and one of sort of the selling points for this second piece is that uh, you have a relatively straightforward way of actually computing this character. Cool. So first for generators, right? I have here an example of a graph that you can build for S4, right? So here I have allowed right multiplication by 1, 4, 2, 4, and 3, 4. And I've pulled out these six elements, right? This sort of subgraph here. I've pulled it out. It's special because it is a coset of a reflection subgroup with generators from the generating set that I used to build that graph. So it's contains 2, 4, 3, 1, and I'm only allowing now multiplication by 2, 4, and 3, 4. I can associate a spline to these elements, to this coset, right? I'm really just going to put Ti minus Tj for the edge that I don't see, right? So I don't see 1, 4. That's the other thing that I used to build that bigger graph on S4. So out of here, you can imagine in that larger one is an edge leaving that's labeled T2 minus T3. So if I put T2 minus T3, it's going to satisfy that edge condition leaving. It also satisfies all of the sort of like internal edge conditions. I can do this for any reflection subgroup, any coset. Uh, and the result in this area is that if the generating set is minimal, right, then I can build my set of coset splines. I'll take every coset of every reflection subgroup. And that set is going to generate my module of splines. It is going to be nowhere near minimal, I should add. There's going to be way, way, way more cosets than the dimension of the space or the rank of the module. And sort of baked into that is if I only take the linear ones by multiplying things together, I can have them as a generating set for the ring. Cool. So this is the generating piece of it. It works uh, really for any reflection group. It doesn't need an associated geometry. This sort of setup is all going to go through. It appears in my paper from a couple of months ago in this context with only type A, but I would claim that there's nothing in there that's type specific, and all of the arguments in there sort of go through uh, regardless of which file group you're working with. So, parts 1 and 2, computing the dot action. Actually going about this is a multi-step process, right? We need to get the dimension or the rank, right? That's usually the first thing. If we have geometry to help out, good for us. And if we don't, we have a little bit more work to do. We need to build a generating set of splines. Now, usually this is going to be, like, in my experience, the easiest way to argue about this is having splines with a very particular support, right? So there's a sort of a special set of permutations or sign permutations that I want to assign a non-zero polynomial, and I'm trying to build the appropriate spline that has that support in order to make an argument about this set actually generating, right? The nature of that, trying to make it match up with the dot action means I'm going to have a set that's too big, right? I'll need to find linear relations within that set to sort of pare the number down until I can get a basis, right? So I want to reduce this generating set in such a way that I now match the dimension that I had computed earlier, but I also want to sort of do away with this whole special support thing. Because if you think about like how the dot action works, it moves polynomials around. So if I want a generating set that plays nicely with the dot action, I can't be particular about what support I have. It has to be sort of uniform. So things that are nice in computing the dot action also tend to be things that are not nice when trying to build a minimal generating set. And that's a huge problem. Um, even just not in this first graded piece. This is like a big problem in GKM theory of Hessenberg varieties overall. And the hope is once the generating set is set up well enough that I can just compute the representation directly. Like it looks like an action or a recognizable action uh, on this generating set. So we'll do type A and type B, type BC separately. Right? So first for type A, what I want to do is have a combinatorial object from which I can just read off the structure of my generating permutations. For that, I'll use a simple graph, right, on 1 through n. I'll let edges ij in that graph be conflated with transpositions ij in the symmetric group, and sort of abuse my notation a little bit and let m sub gamma be the module of splines that I get out by using all of the edges that gamma gives me. Right, so what does that look like? If I take the complete graph for gamma, that's going to give me all transpositions. That's like the flag variety, full flag variety case. If I take just the path graph, that's going to be the simple transpositions. That's the permutahedral variety case. And if I want to have an associated geometry, the graph gamma that I'll need to use is a unit interval graph, right? Or a Hessenberg graph. That's what's going to correspond with a geometric case. But the result I'll share with you for type A, and my contributions to this are in the non-geometric cases when we don't have this setup, right? For any simple graph. So what does this look like? Again, my contributions are sort of in the non-geometric examples. In the geometric case, when we have that unit interval graph, the linear representation, the first piece of our graded representation has been computed in a bunch of different ways. Geometrically, with GKM theory, in the chromatic symmetric function land. We were able to do this for any graph, right? And so the big takeaway is that this first graded piece can be computed totally combinatorially from the data of cut edges and cut vertices and the separated components thereafter in the graph gamma. This is the formula itself is like sort of technical. It requires some non-trivial structure theory, like the block cut diagram of a graph, but it's not so bad to show in an example, especially for a tree. I have here associated to every edge in a tree, so every edge is a cut edge. Specifically in tree land, I'm not going to have to worry too much about cut vertices. I've associated the pair of numbers, uh, giving the size of the two graphs that removing that edge cuts it into, right? So if I remove this edge, I'll get size 4 and size 4 for this side and this side. I need one sort of special one that just gets all 8, a leaf, if you will, that gets all 8. And the graded character is the character summed up for all of these edges of the action on cosets of subgroups of this type, right? So I have this 4, 4, I get it from my edge. That's associated to a little S4 cross S4 sitting inside of my S8. The S8 action on cosets of that is a permutation representation, and I get a copy of that in my representation from this edge, essentially. The real takeaway is that you can look at these edges and, maybe if there's a cycle, some of the vertices, and just pick out which permutation representations and uh, that exist in this first graded character just from the structure of the graph. For types B and type C,
Could you say again, why is that 8 special? Why is that not a 7, comma 1?
So upstairs in the vector space that is the first graded character of like the mod what am I thinking? Like the module of splines before we do that quotient, it is a 7-1. But we
Okay.
lose, well, it's associated to a piece that we kind of lose by taking that quotient is maybe the best way I can describe that.
Okay. Okay. Thanks.
Oh, and like the I guess maybe more specifically, the linear relations that I use to cut down mean that the splines that would normally be associated to a 7-1 here have linear relations that get them removed. And I'm left with just something that's acted on trivially. I don't know if that was more helpful, but it's true. Um, cool. Oh, so for types B and C, right? We're working in signed permutation land. I'll let pi, just because I used ti already, be the transposition that switches I and I plus 2, unless I get too far towards n, and then I'll use Pn minus 1 for negating the n minus 1th element, and Pn for switching and negating the last two. These are just all of the length 3 transpositions in the type BC vial group. Like they're all Si plus 1, Si, or Sn minus 1, Sn. If we take all of those collections together in the connected, I should probably say, type BC geometric cases. So the sets of transpositions that we have spit out from a regular semi-simple Hessenberg variety, right? The first graded character is entirely determined by which one of these transpositions is contained within the set of transpositions that we get out of our Hessenberg variety, right? So I can compute everything I need to know just from which one of these I see showing up, right? So the first thing this allows us to do is unify type B and type C calculations, right? This is not the crowd that I need to really zero in on this on, but type B and type C are very different, despite them having the same vial group. But this sort of structure allows us to do essentially the same sort of work for both type B and type C in this case, right? It gives us a condition for equality, right? As long as this intersection is the same, two different sets of transpositions are going to have the exact same first graded character. And I do want to mention that the type BC distinction is specifically with these last two. So type B and type C have different root posets. And so I'm allowed to have one of these and not the other, specifically in type B or type C. So there are some choices to be made here where that difference is actually like readable. Cool. And well, what's the theorem in this case, right? So in this geometric case type BC, this first graded character, it's totally computable from this intersection. And it's not a complicated, it's in the similar flavor as the type A result. There's not a ton of crazy combinatorics that you have to do after seeing this intersection. You can sort of just read off pieces of the representation that you get from the data of this intersection. So you'll get some number of trivial representations sitting inside of this, right? That's going to end up being associated almost exactly to just the size of this intersection, how many of those length 3 transpositions I ended up using. Right? We get actions on reflection subgroups for almost everything else. Again, just associated to what elements are contained within the set of transpositions that I'm working with, just intersection conditions. Right? With a little bit of funny business on T. Oh, these are all supposed to be P's, P sub k minus 1. Apologies on that. These are the length 3 transpositions that we saw before. On whether or not Pn is in this set versus Pn minus 1, there can be little small differences there. Right? So this is great, right? We've computed all of these first graded characters. One of the interesting things that shows up for both of them is they're all permutation representations acting on reflection subgroups. Now that's definitely interesting in the type A case for like Stanley-Stembridge conjecture graded Stanley-Stembridge conjecture reasons. And it's interesting to show up in the type BC case because we sort of don't have, or at least there's not really a lot of agreement on what a general type conjecture is in types B, C, or D for that. I will mention all of these under, if you know what the Frobenius character map is, these all spit out H positive things, which is sort of interesting. I know this isn't a permutation representation on a reflection subgroup, but we can package it with a trivial representation in every case and get that sort of behavior. So there's a ton still left to do, right? If I wanted to sell myself on this, I'd say there's a very active research area. There's tons of questions out there. In the type A case, in the type BC case, you might have noticed perhaps like a suspicious lack of type D results. Turns out getting dimension in that setup is sort of difficult because of that Sn minus 2 simple transposition having sort of too many things it doesn't commute with. It makes computation a little bit more difficult. But overall, lots of things to look forward to. And thank you for listening to me. I have a bunch of references that'll be in slides when things get shared, but thanks for having me. I'd love to answer any questions.
Thank you very much. Thank you for a beautiful talk.